All right, good morning, everyone. Like Kotloigo mentioned, I'm Daniel van Zyl, and I will be talking about evolutionary algorithms and try to answer the question if they can be used to speed up the software development lifecycle. So without further ado, let's jump into it. So just a quick overview. What is an evolutionary algorithm? So an evolutionary algorithm is basically a machine learning algorithm based on the theory of evolution that is commonly used to solve optimization problems. So it's been used to solve stuff like the traveling salesman problem, timetabling, bin packing, things like that. But I'm trying to see if I can use it to, speed up the software development lifecycle. So some of the advantages of evolutionary algorithms above something like deep learning is they're computationally less expensive in a lot of cases. They can require less input data to produce promising results. Those of you that know neural networks and deep learning, you need a bunch of data to actually train accurate models. So with evolutionary algorithms, you need less. And the last thing that I think is a big advantage is its representation is easy to understand and much easier to understand than some deep learning architectures. But as with everything in technology, there is disadvantages as well. So a lot of the times, evolutionary algorithms, they converge prematurely. So what that means is they think they found the optimal solution way before they actually is close to it. So to design them in a way that to prevent that is the tricky part. Also, they're very problem specific. So the design of them is not something that you can design once and implement and use across everything. You can do that, although it is definitely much more complicated. And then as the program or as the problem that you want to solve becomes more complex, the dimensions of the problem obviously increases, and this, as such, the search space actually increases as well, and it makes it difficult for the algorithm to actually navigate the search space properly and efficiently. All right, so then the two evolutionary algorithm versions or variants that I quickly want to talk about is a genetic algorithm and genetic programming. So a genetic algorithm, well, for all the evolutionary algorithms, so how they work is a solution to a problem is represented as an individual, and a population of these individuals are created. And then the algorithm starts evolving them. So by applying some genetic operators to that, I'll get into a little bit of more detail once I get to the demo of how this actually works. So the difference between a genetic algorithm and a genetic program is genetic programming actually evolves executable programs. So it can be functions, code, well, anything essentially. And the individuals is represented as syntax trees. So you're actually busy building trees and traversing and swapping nodes around. So yeah. Anyways, today I'm going to focus on the genetic algorithm. So it's fairly straightforward, the algorithm itself. So obviously you start off by creating this initial population. This gets created totally randomly. So first, before that, you need to decide how are you going to represent your individuals. So in genetic algorithms, they're represented as chromosomes, and the chromosome have a number of genes. We'll show you my representation just now. Then after that, you need a way to determine how well the individuals actually solve the problem at hand. that's where your fitness function comes in. So the fitness function is just a function that evaluates how good the solution actually is. Then after that, there's selection, which selects parents to produce offspring for the next generation. Offspring is produced by genetic operators, and the two most common ones is crossover and mutation. So crossover is simple. It just selects two parents, and it actually literally cross over a part of the two genes or part of the chromosomes of the parents. Mutation is used to introduce new things. So if it's just a binary string, maybe swapping some or flipping bits. So yeah, and then this process continue until some termination criteria is met. Usually it's a number of generations or something like that. All right, so now the question is, how can we use it to speed up the software development lifecycle? And initially I had these 4 thoughts that came to mind. Is 1, code refactoring, the second one, code optimization, and then test case generation and task scheduling. I decided to dive a little bit deeper into test case generation because I don't like thinking of all the edge cases when I need to test my code. So getting something that can spit out a bunch of test cases and I can just run that would be pretty sweet, and obviously speed up some time there. All right, so let's jump into the demo. So first of all, I have my GA set up here, and it's basically, I have 5 functions that I want to generate test cases for. They're not useful in any way, the functions themselves. They're very, silly, but I thought it might be a cool or good way to actually just show that there is some power in genetic algorithms. So I have 5 of these functions that just looks at random combinations of the input integers. So I have 5 of them. And before I get to the fitness, let me quickly show you how I'm representing my individuals. So like I've mentioned, there's a chromosome, and each chromosome consists of genes. So my chromosome, for this case, is a fixed length of 5, and in each gene, there's a bunch of test cases. So that can be visible. So yeah, I think it's, in this case, up to 24 test cases per gene. All right, so that is my representation. Then obviously the fitness. How am I actually measuring how well the test cases is performing? So I've got my fitness function over there. So essentially all that it's doing is it takes the test cases, it runs it through the respective functions, and it counts how many of the strings got actually hit. All right, so if you think like this one, there's 7 possibilities. So essentially it just calculates the average or the percentage of string or outcomes actually hit. And there's 5 test cases, so essentially the ideal, and it sums it up. So the ideal fitness for this case is 5. So I want 100% coverage for all 5 functions. But then I thought, okay, that's great. I can just brute force this and implement or test 1,000 test cases, and hopefully I get 100% coverage. But that's not that efficient, so I introduced a penalty. So essentially the penalty, what it's doing is the higher or the more test cases you use, the you'll be penalized on that. So essentially the fitness function tries to balance the coverage as well as the amount of test cases used. All right, so Then I mentioned the genetic operators, crossover and mutation. So just a quick summary of how it works. So let's say you have two parents there. Those are the test cases, and they're selected to undergo crossover. Then obviously for the first parent, a crossover point is selected, and the two parts of the parent just get swapped. So if one of the children would be 10, 21, and 2, and the other one would be, negative 1967 and negative 89. I just showed one example. Then mutation, if something is selected to undergo a mutation, essentially it just increases or decreases the values. I decided on either -5 +5 or -1 +1. So yeah, that was how I decided to actually design my genetic algorithm. And now let's actually run it to see how it actually, from the first generation, to see how that evolution takes place until the last generation. And in this case, I believe it's 50. All right. All right, as you can see, it's running pretty quickly. And there is the fitness over the time. So as you can see from the first generation, I don't know whose phone is that. So from the first generation, you can see it actually increased over time. However, all of you will notice something happened just around just after the 10th generation. The algorithm converged and it couldn't find an improvement. So that's where the challenge comes in with evolutionary algorithms. Is there's a couple of parameters that you have to tweak, and you have to try and find the best combination of them, and obviously each parameter affects the other one. But yeah, that's essentially what I did. I can quickly show you what will happen. So if I increase the generations to 100 and run that, luckily it runs pretty quickly. So as I mentioned, the optimal fitness is 5. All right, I'm getting 3.3, so it's not the best, but remember there's a penalty involved as well, so the fitness is not purely coverage. So if you take out the penalty, hopefully from previous tests it looked like I get around 80% coverage from just numbers. And I mean, if all of you will take your time to determine the combinations of all of this to hit every single one, it will take a significant number of time. So, do I think evolutionary algorithms can speed up the software development cycle? I do. I think there is a potential. Obviously, this is still in the very, very early stages. There's a lot that needs to be done, a lot that needs to be tested. But yeah, I do think the potential is there, and I find evolutionary algorithms pretty interesting. I think it's essentially survival of the fittest in code. So that's something that I pretty much enjoy and think it's a cool concept. So yeah, is there any questions? Dino.